Welcome back to the AP Chemistry series. So, today I'll be talking about the Bohr model of the atom and a little bit more about emission spectra. Alright, so getting started. Briefly, a while back, I introduced something known as the Bohr model, and it's also known as the solar system atomic model, right? It requires that electrons move around the nucleus, and this is the nucleus, right? It requires that these electrons, which I'm going to box again, move around the nucleus in specific allowed orbits. So using classical mechanics, which remember has been replaced by quantum mechanics, but when Bohr did this, when Niels Bohr, the scientist who made this model, did this, he calculated that the energy of an electron in an orbit with a number n, so this number n over here, and I'll give you an example. So the first orbit is numbered 1, so it would be this circle. And similarly, the second one, the second orbit, would be given the number 2, and it would be this circle. So an orbit n would just refer to the nth circle. So when we're talking about an electron in the nth circle, we're saying that the energy of an electron in an orbit n is this. It is negative 2.178 times 10 to the power of negative 18 joules divided by n squared. And this is a formula that you don't need very often, but it's very good to memorize because it gives you an idea about electrons moving around in the atom. So now, back to what we started covering last time with Planck's equation and the other equation that I talked about, wavelength times frequency is equal to the speed of light. Alright, so look at these electrons over here. They're floating around this atom in this circular pattern, right? So what happens if an electron over here jumps down? It loses energy and it jumps down to over here. What do you think would happen? Pause the video and try to think about it. I covered it a little bit last time, but I'll give you a second to think about it. Well, what would actually happen is there would be a photon released, or photons released as light, right? This energy would be emitted as light because energy can't be created or destroyed. And since this electron, which is in a higher energy state than this electron, because it's farther away from the nucleus, right? When it goes closer to the nucleus, it's losing energy. And since it can't just destroy that energy, it needs to be sent elsewhere, and it's expelled or emitted as a photon. And the cool thing is that we can actually measure the frequencies of light and the wavelengths of light that are coming out of these electrons jumping. So for example, let's look at the same electrons. Let's say this one jumps down there. When this electron jumps down, it releases this photon, and we can actually look at the wavelength of this photon. And if we take, for example, this number line over here, and on this number line, we can actually plot the wavelength, okay? So for example, let's say that there's an electron over here, and this is fake data just for learning purposes, jumps down over here. So let's say this electron jumps down over here. And then let's talk about this electron jumping down over here. So since they're both jumping differently from different areas to different areas, they're going to release different wavelengths of light. So remember, if the jump between orbits is the exact same, so if you're jumping from the same orbit to another orbit that is also the same, then the energy that is released and the photon that will be released is the exact same. So if you're jumping from orbit 4 to orbit 2, anytime an electron does this, it is always going to release the same wavelength of light. But, for example, an electron jumping from 4 to 1 will release a different wavelength of light than, for example, 4 jumping to 2, like we talked about, right? Or, for example, 3 jumping to 1 is going to release something different than 4 jumping to 1, or even 4 jumping to 2, all right? And that should be a 1 there, right? Okay, so back to the idea of our number line. On this number line, let's say that this electron over here, jumping down to this electron, and I'm drawing a lot of arrows, so it's getting a little messy, but that jump, let's say that it releases light with a wavelength of 700 nanometers, and this would actually correspond to violet light. But this is fake data, by the way, right? We're not actually considering real data. This is just for learning purposes. And then let's say this jump over here, from this electron jumping down to this electron over here, releases wavelengths of light that is, for example, 400 nanometers. All right? So what we can do is, on a black backdrop, like this black backdrop over here, we can color in a line. Do you see these lines and this line? We can color in a line that corresponds to those wavelengths. So for example, at 400 nanometers, we can color in a red line like this one because 400 nanometers corresponds to red. And at 700 nanometers, we can plot something that corresponds to violet. Do you see these lines? And hopefully you're beginning to understand how these lines represent the wavelengths of light that are being emitted from these electrons jumping around in this atom. Okay? So when you energize an energize an atom and then let it come back to its ground state, when the electrons emit their light, this is going to be recorded in a data table or a data graph or visualization, depending on where you're from. It can be recorded in something known as an emission spectrum. And this over here, all of these are emission spectrums, all of these in black. And I'll start clearing the screen so that you can see them better. For example, this one is for hydrogen. If you take a sample of hydrogen gas and you pass an electric current through it just to energize the electrons in it, to excite the electrons in it, and then you let those electrons jump back down all around, you'll notice that these are the wavelengths of light that you'll be noticing. These are the wavelengths of light that the electrons in the hydrogen atom are emitting. And it's not going to be the same for any atom. So for example, hydrogen electrons are going to emit different wavelengths than helium electrons. And similarly, sodium electrons are going to emit different wavelengths of light than neon electrons. All right, so this is very interesting because it makes each element have its own signature. And from an atom's emission spectrum, we can actually try and identify which element it is. And it's very interesting. So this was part 1 of this topic, and I'll cover more about it and how we can quantify this using energy and Planck's equation very soon. All right, I'll see you then. Bye-bye.